Hello everyone. Today is my day 3 of the challenge, and today I will be discussing about the standard template library STL. So STL is the most important part in the data structures and algorithm where there are pre-implemented data structures and pre-implemented algorithms which we use. So the flow of the explanation for today will be, firstly we will discuss about the containers, then we will go to the iterators, that how the iterators work on the containers, then we will see that how the algorithms work, how they perform the operations on the data. So this is just a flow. We will also see that whenever we are firstly we will have the basics of the containers, then we will discuss about the iterators, and we will discuss that how these work on the containers. So at that time we will also discuss more about the containers, and when we come on the algorithms, then we will see how the operations are performed on the data which is stored inside the containers. So these all things will just be explained as a mix. Okay, so the simple basics of the containers is like that container is something, it's a pre-built data structure, and it is something where we can say a type of storage where the data is stored, or we can say where the data lives. So they can be of different types like vectors, arrays, list, set, map, stack, queue. Likewise, now the iterators are the pointer like objects which points to the data, where the to, which we can say which points a particular position where the value is present. So it's like how we walk through the data which is stored inside the containers. Then the algorithms are there. So it's like what we can do with the data, whatever the data we have stored inside the container, what operations we can perform. Like we can sort the data, we can reverse the data, we can find the maximum element, we can find any element, we can like search any element in the container where we have stored the data. Okay, so now firstly coming to the containers. So container, as we have already discussed, that containers are the pre-built data structure in the C++ where the some elements are stored, where the data is stored in a specific way. So there are different types of containers where they are having a specific purpose, that what is the purpose they can do. Okay, what things they can it's like what is the use case of the containers. Okay, and a way of the storing the data means different data containers are there, like vector array, they are having their separate uh, like way of storing the data. Okay, and time complexity is guarantee, like whatever the operations we are performing, so what cost they are taking, what time complexity they are taking, that's the container can have, and their specific use cases. Okay, so firstly coming to the pair is simply it's a simple container, we can say, which is having exactly two elements. So here we have already written here that pair int comma int p, and here 2 comma 5 are there. So exactly two elements are there. Now whatever the data type we write here inside this pair, so it can be same data type, it can be of the different data type, like it can be also intent, it can also be int comma string. So that depends how we are using it. And this pair is defined inside the utility header file. Okay, as mentioned here. And now we have just seen that it can store, or it can just have the exactly two elements. But what if we have to store the multiple elements in that? Let's say I have to store three elements in this. So what I can do, see, I already know that it can have two types, like int comma int. If I have to store three elements, let's say 1 2 3, so it can have one int comma int. In that way I can just give 1 comma 2 inside the curly braces. Now if I want 1 comma 2 comma 3, if I have to store there, so I can just take one of type int and second of type pair, because second can take another two elements. Just I have mentioned in this particular block, that we can write in this way: pair int comma pair int comma int. So in this int it can take one element, and then in this pair it can take another two elements. So this is how it will take three elements. This is how it works for the multiple elements. Now as we also know that the array of integers is there, like it can take in multiple elements of the integer type. Okay, so just like that, it can also be of the type pairs. It means the array which is of integer type when we write, or any let's say characters, so it can also be of the pair type. It can be written in such a way that the data type can be written here, parent comma int, and this array, and then we can give the elements in the form of pairs. Now if you have to access these elements, what you will do is, we know that this is the 0th index, this is the first index, so we can just go at 0th index using this indexing, like arr of 0, and then inside that particular, now we are at the 0th index. Now this is a pair, this is not an element. So after going at the 0th index, we will just take the dot second. It means when we go at 0th index and when we do dot second, it will give us 2. This is how it works. Okay, now we have seen what the pair is, a simple container. Okay, now coming to the container vector. Vector is a container which stores the elements contiguously in the memory. It means, see, whatever the elements are stored inside the vector, only the first address of the first element, its address, we don't know where it will be in the memory, but whatever the elements are present after that address will be in the contiguous manner. Okay, let's say if a element is there, if a vector is there and its first element is placed at the in memory at a particular address, let's say 200. Now we cannot know that what is the memory in the memory, what the address is for the first element, but after that whatever the elements will be, they will be in the contiguous manner. So this is what the vector is. And the important thing about it is different, what differentiates it from the array, that it is having the dynamic size. We can increase the size. It increases the size at runtime. So if it is, the vector is full and we have to push any element at the end, then we can do that. Okay, which is not available in the array because it is of fixed size. We cannot change the size of the array. So the operations which I have just mentioned here, what I have just said, that vector means the fast access and the fast pushback. It means at the constant cost, at the constant time, we can add the element at the back, and also fast access because of the indexing. Now, but not good at the insertion or the removal in the middle. So it means that if we have to insert any element at the middle of the vector, now we cannot do it in the fast manner, because when we are inserting any element at the middle, and whatever the elements are present at that particular index where we have to insert, the elements starting from that index till the last index, they all elements has to shift towards right, and this takes time, and so it is a slow process in order to insert in the middle or remove in the middle. So this is why it is not vector is not good at insertion or removal in the middle. This is what it means. Well, I have also just mentioned all these points. You can just read from here. Now, seeing some of the operations, sorry, functions inside the vector, how we use. So dot pushback is used just to add the element at the end, and dot emplace back is also doing the same thing, but it is somewhat faster as compared to dot pushback. Okay, and inside the vector, as it can be integer data type when we write the like vector, it can also have the integer values, but it can also have the values of pair form, which we have already seen, or what the pair is. Okay, and after that we can also use using pushback. If we are pushing a pair, then we will have to use the curly braces, but if we are using dot and place back, then we need not to give the curly braces. We can simply write 1 comma 2. It will understand that yes, it is inserting a pair in that vector. Now, if we are writing this line, vector int and v of 5 comma 80, it means we are saying that take the 5 positions and place 80 at every position. And this is how the array will look like when this particular statement is executed. Now, vector int v1 of v, it means whatever the vector v is there, it will be copied inside the v1 vector. This is what it means. Some more functions about this. If we are using v dot end, v dot end means whatever the vector is, whatever the number of elements are present in the vector, the last element, the it means the position after the last element, just next position after the last element, that is the v dot end. So it is the position after last element. V dot back means it is the last element itself. Okay, and if we are using v dot arrays, using v dot begin plus 2, it means we are saying that go to v dot begin in the vector, go at the beginning position and go to index forward, just erase that particular value from. And v dot begin, if we are saying this, it means we are giving a particular range to this, that go at v dot begin plus 1 index and the index v dot begin plus 3. So v dot begin plus 3 is the index. We are saying that start from v dot begin plus 1 and go one position less from v dot begin plus 3. That's the meaning of this. It will erase that entire particular values. Okay. Now v dot insert, v dot if we have to insert any element, so we can just go at v dot begin. It means we have to insert at 0th index, so we can just use this particular function dot the insert function, and inside this we will give v dot begin comma 100. I have to insert 100 there. Okay, and v dot insert v dot begin, it means we are saying that we just go inside the v dot begin plus 1 index, and from there for 2 positions place 5 there. This is the meaning, means insert 5 there at 2 positions. Now v dot size gives the size of the vector. V dot pop back, it just removes the last element from the vector. V dot swap v1 means the vectors v and v1 will be swapped using the swap function. V dot clear, it just clears out the memory. Okay, whatever the vector is taking, all the elements. And v dot empty, it just gives true or false. If the vector is empty, it will give true, otherwise it will give false. These are some of the operations we have seen for the vector. This point we have already discussed, that v dot pushback means we are pushing the element at the end of the vector. Okay, so it is taking no any shifting, no any rearrangement, so it just takes constant cost, a constant time, we can say. Now one question is there, that why the insert operation at the front or the middle is slow. That's we have already discussed, that in the middle, when we are inserting any element, it means all the elements starting from that index where we are inserting, all the elements will be shifted towards right. So that's why in the worst case scenario, it can take big O of n time complexity. Because just think of, if we are having 1,000 elements and if we have to insert the element at the 0th index itself, then all the 1,000 elements has to be shifted towards right. Okay, this is the it's the mean that's the meaning, simple. That's why it is slow process in vector. So we do not just use the vector in such things. Okay. Now coming to the second container, that's also important one, that is list. And also we will see the difference between the vector and the list. So firstly, the list, it is std colon colon list. Std, that is the standard namespace. Okay, so a list is simple. List is just a pre-built, which is, we can say, a container inside the standard namespace. So basically list is it's in itself, it is a doubly linked list. Okay, so here every element is stored, whatever the element is, in its entire the entire element, it consists of the value, it consists of the pointer to the next node, it consists the pointer to the previous node. And this is what we can say, that it is not a contiguous in memory like the vector. Okay, so because the every node is scattered, all the nodes in the list are scattered at different addresses in the memory, so we cannot say it is contiguous. Okay, that's the meaning of the list. Now why is list faster for the middle insertions? Here comes the difference, that vector, we already seen that it is stored contiguously in the memory, and in the insertion in the middle, it just it just cost a big O of n. Okay, but in the case of list, because it is having the linked nodes, and if we have to insert any of the any element, we can simply just we have to do two things. We have to just change the two pointers for the next node and for the previous node. That's all it needs. So it takes the constant cost, no any uh, uh, it is not taking much time. It is the constant cost itself. So that's why the list is faster for the middle insertions. Okay, now let's see the difference between the vector versus the list. That's same as I have already discussed, that vector is elements are stored contiguously, and a list is basically a linked list, but here the nodes are scattered, okay, at the different addresses in the memory. Now in the vector, if we see that I want the 500th element, okay, so what I will do, like at the 500 index in the vector, so what I can do, simply I can go at the start address and do it's just a formula, that plus 500 into the size of the element, it will take me to that particular index. But in list, what happens that if I have to go at the 500th element, I will have to move one by one step at a time, one node at a time. Okay, so but here, okay, as of now I have just told that the list is uh, important if we have to if we have to insert in the middle, if we want the middle insertions, so we can use list because it is faster. But list is not always like we do not consider list always, because at some point of time we want the fast in accessing. So in that case, we will have to use vector because it is instant. It is constant cost, it is having constant cost, so we can just directly jump using indexing. But in the list, in the case of list, we will have to just move one node at a time, so it takes big O of n time. Okay, so here, fast random access, constant, slow insertion in the middle, big O of n. It is best when we need indexing, already I told now. And list is slow at random access, big O of n. Fast insertion or removal in the middle, big O of 1, that is constant. And it is best when the main work is of the insertion or the deletion. Okay, that's the difference. Now coming to the another container is the dq. So dq is a doubly ended queue. In a is a that's a container. Doubly ended queue means it is having two. We can just think of the two gates. uh, we can just think that there is a line of people, and one gate is at the front, one gate is at the end. Okay, it's like that. And these all operations are the same, like push front, push back, pop front, pop back. Okay, because it is a doubly ended queue. All the operations are the fast, they are the constant time, and it's a queue, but the extended version, we can say. Queue is what the queue is having the front end and the rear end, where from the rear end we do the insertion, front end from which we do the deletion, but it's a extended version, that's a doubly ended queue. So here, now let's check the difference between the DQ versus the vector. So vector, we already know that fast push back only, means we can push the element from the back itself, at the from the end. But DQ is one in which we can push front and also the push back. Now versus the list. So list, we already know that the fast insertion anywhere, at the middle, at the first, at the end. Okay, but it is slow access, we cannot access fastly, because it is a list which is not contiguous in nature in the memory. But in the case of DQ, it is fast at both the ends. It means faster random access than the list as well. So DQ, here we can say that DQ sits between the vector and the list. Okay, so that's why it is written here that vector less than DQ, then less than the list. So DQ is something which we use between the vector or the list, according to the uh, work we have to do. Okay, now let's get to the another container, that is set. Set is another important container in which it is implemented. It is implemented as a balanced binary search tree, or usually say as a red black tree. So this means every operation where insertion is performing, deletion is performing, searching is performing, they all takes big O of log n operation, big O of log n time. And here the important property is set is the set is a container in which the elements are stored in the unique fashion and also in the sorted fashion. The duplicates, whenever, let's say, even if we give the 100 times a particular value, it will store only the single uh, number of that particular value. If we are even giving the multiple duplicates, it will just store its single entity. Okay, so the duplicate values are automatically rejected even if we give the multiple duplicates. So set is something like, it is a combination of the sorted elements along with the unique elements, and with the log n operations, whatever we perform, insertion, deletion, searching, all that. You can just have a like real world analogy, that you can just imagine that you are building a browser history feature, and there is a back button which removes from the back, there is a forward button which adds to the back, and sometimes the user has to jump to the start, or like go to the home page, or let's say sometimes the user pages are removed from the front. So in that case, the set is used. You can think of a real world analogy in that way. Now, another is the unordered set. It is just different from the, just a small difference from the set, that it is having the unique elements, and it is having the unique elements, and also but the order is not here. As we see in the set, it is having the sorted order, but here the no order is there about this. Unique elements are there, and important thing is that it is having fast hashing because it uses the hash table. So no duplicates are present here, no sorting is there. It uses a hash table as an internal structure, and the operations are constant because it is using the hash table. So whenever the element is going inside the hash table, it is basically goes with a hash key, or we can say a label. So whenever, so already we know that whenever the element is going, it is going randomly. There is no any order for that, but it is going with a hash key. So whenever we have to access it instantly, that is faster in the case of unordered map. Unordered set. So that's the important feature of this unordered set. Operations are constant and very fast for lookup, insert, or delete. Okay. Now some of the features, just the difference between the set and unordered set, just to have a quick recap. That in the set, the elements are sorted, yes. In unordered set, they are not sorted. In the set, they are unique, and also in the unordered set, they are unique. Internal data structure for the set is a red black tree, because of which the time complexity goes to big O of logging. And in the case of unordered set, the internal structure is hash table. So because of the hash is used in order to place the elements inside the hash table, and after that, when we have to access, it takes constant time. And set is best for when the order matters, but when speed matters to us, we don't care about the order, so we can use unordered set. So this is why the unordered set is extremely fast. Now coming to the another container, map. So map is a container that stores the data in key value pairs. Now map is something we can just we can just connect it with the set. But both the set and the map are used as a they use the internal structure as the balanced binary search tree or the red black tree. So the operations, like we have to any search operation, we have to perform any insert or we have to erase anything. So we can just that's the big O of login time it takes. So map is, we can just think of as a sorted dictionary. Like you can just think of that there is a contact list which is sorted alphabetically. Now each contact name is a key and the phone number is a value. Now if you are because the map is something where the uh, elements, or sorry, they are stored in the key value pair, so the keys must be in the unique fashion. And in the unique fashion, so whenever we cannot have the two keys, we cannot have a like you cannot have the two contacts with the same name. So if the keys are same, let's say the same name is there and for them two contacts are there, it is invalid. So you cannot have the two contacts with the same name. Everything stays sorted automatically. Okay. Now unordered map, again, that's the fastest dictionary we can say. So here it is, the key value pairs are there, but it is very fast also, because here the hash tables are used internally, same as the unordered set. Again, it is not sorted. Okay, you can just read that here. It is same. Now we need to traverse in the ascending key order whenever we have to traverse, and here we need the lower bound and upper bound. We will see what the lower bound and upper bound are in the further in the video. And we want the predictable order in the output. Whenever we want, we use the map. That's the difference between the map and unordered map. Whenever we have to traverse in the ascending order, ascending key order, or when we need the lower bound, upper bound, when we want the predictable order and output, we use the map, because it is having the sorted order. It is when the speed do not matters to us. So we use this particular container, and which having the internal structure of the red black tree. And when the order matters to us, but speed doesn't matter, so we map. And we use unordered map when we care about the speed, because it is having the constant speed. Okay. And order when doesn't matter to us, because it is unordered, and we need the fast counting or the lookup, we just use the unordered map. Now there are some more containers I want to discuss before coming to the iterators. So some of the containers are here. Okay, some more containers are present here. That is a stack queue, priority queue, multi-set, multi-map. So a stack queue and priority queue we will discuss more in the depth also, because they are also known as the container adapters. It means they are itself having some of the underlying containers of the STL. Okay, and then the multi-set and multi-map. Firstly, come to the stack. Stack is simple, a data structure, a container which is having the three operations itself, only the push, pop, and the top operation. So stack is something where we can like it follows the LIFO principle. The last and first out means the element which came at last, it will go out first. Okay. So it is again it is written in such a way that stack int and st. And then if we have to push something, we can use the push function. To pop, we can use pop function. And if we want the element from the top, we can simply we can use the top function. Now these all the operations are taking the constant. These all are constant. Okay. And here no any shifting can be done for the element. No any uh, like we no need to shift anything, or no need to any, like in the middle, no any operations just takes place. The only push, pop, and top operation. Now secondly, coming to the queue. So we will also see more about the stack here. And then queue is where we have to insert at the rear end. So it is having the queue, like it follows the FIFO principle, first in first out. And just you can think of the line at a counter where first person who comes in will go out first. Okay, so here if we have to any insert any element, we can do at the rear end. That is again constant operation. If we have to ever remove any element, then we can do from the front. That's again constant. If we never have to shift the element, so again constant. And we don't have to search, so that's again constant. Now priority queue. Okay, so priority queue is see, priority queue is a container where it is having like two forms, a kind of heap, max heap and min heap. Max heap is something which is having the which it just follows the tree like structure in itself. It means in the max heap, the priority is by default using the is having the max heap, that the top element at the root node, it will be the greatest element, and in the min heap the top element at the root node will be the minimum element. Now on the root node, only the root is guaranteed to be correct, like maximum or minimum. We Two things are there in the priority, sorry, two things are there in the heaps. One is the heap sort, but another thing is the like priority queue, which is the min heap or max heap. So it's just a difference between those is that we are that in the heap sort we can sort all the number of elements which are present. Those all the entire elements are sorted, but in the priority queue as a heap, what happens is that only the element which is present at the root node is guaranteed, that yes, if we are using the max heap, so it must be maximum. If we are using the min heap, it must be minimum, and rest of the elements are also stored, but their order doesn't matter. Their order is like they are not in the sorted order. So if we are saying that can we tell about the second largest element in the heap, let's say in the max heap, if the first largest element is there, can we say something about the second largest element? No, we cannot. We can't say, because we have the guarantee that the root node will be having the maximum element in the max heap, but we cannot say about the order of the rest of the elements. They are just stored, but they are not in the correct order or in the sorted order. So the second largest is not guaranteed to be the left child. Now a heap maintains the partial order, not the full order. Okay, that I have already explained. You will also understand about this priority queue when we come later to the container adapters. Now coming to the multi-set and multi-map. Multi-set is let's say this is a multi-set, and again, as we talked about the set, it is just a simple difference from the set. The set is having the sorted and the unique elements. Okay, but in the multi-set, what happens is that it is having sorted, but the duplicate elements can also appear next to each other. Okay, this is the difference only. The multiple duplicates can come here. Rest all the things are same. It is using the balanced binary search tree like the set, but allows the multiple identical keys. Okay. Then it is again still the log and operations are there, still tree based red black tree we can say. Okay, no indexing is there like the set, and iteration is in sorted order as we have already discussed. Now simple difference between the set and multi-set. So features are simple, that in the set, yes, it is sorted. Multi-set, yes, it is sorted. In the set, no duplicates are there, only unique elements are there, but in the multi-set there are duplicates. That's only the difference. And log and operations are required in both for the insertion time and in the arrays. In the set, all occurrences or iterator, like when using the arrays feature, that we will just see what happens with the arrays. And single instance possible in the multi-set. Okay, because in the set all occurrences or the iterator, because only one element, unique element is there, so when we erase, that will be deleted. But in the multi-set, if we are using any particular erase function directly for our element, then it will erase all the occurrences. But if we have to delete the single instance, so it is possible in multi-set. Now set is best for the unique elements and multi-set is best for the duplicate heavy data. Simple. Now this is the thing which I am talking about, the feature of erase function. If we are using the erase function directly, it means if I am not using the ms.find here, I am directly saying that I have to use this ms.erase, and I am directly giving the value inside this, let's say 5, and if any if any value is there, and just as we have seen this, this is the multi-set, let's say, so here two fives are there, those all will be deleted because I am giving directly. If I don't want this, I can use this ms.find, that you find the first occurrence of 5, and it will just return the iterator to that particular position, and that value will be deleted then. Otherwise all occurrences will be deleted. That's the question I have simply asked. What happens if you call ms.erase of 20? So if any value is there, there are multiple 20s, all the occurrences of 20s will be deleted. Otherwise, if we have to only delete from one instance, then we can simply use this particular function. Okay. Now coming to the map versus the multi-map. Again, as we have talked about the map, multi-map is simple, that the unique keys are as we have talked about the map. Like what is the map? Map is having the key value pairs where it is having the sorted order, and in the map there are unique keys, but in multi-map there are the duplicate keys as well. That's the difference written here. This map is sorted, multi-map is sorted. Unique keys are present in map. In the multi-map, no. Duplicate keys in map, no. But in multi-map, yes. So lookup for this map is login, and in multi-map that is again login. That's all the same things. So when we want to use the unique entries, we can use map, and when we want the group entries like duplicates can have duplicate keys, then we can use multi-map. Again, erase. If we are in the multi-map, if we are using erase and key, then it removes all the entries of that key. If we want to remove only one entry, then we can just use this. We have to find that key particularly, and then it will give the iterator, and going to that position, it will remove that specific entry. You can just think of it as the university database, like multi-map, like if the two keys can be there, that may be duplicate. Okay. Where the values of this, let's say in the university database, let's say a student is having the marks for the multiple subjects. So let's say in one subject got 90 marks and another subject got 95 marks. So that can be stored. That's a kind of university database that we can relate to it. So it's like auto, we just write in this way: auto start, okay, and using the lower bound, and auto end using the upper bound. We can get all the entries for that particular key. In the multi-map, the keys can be multiple, means duplicate keys. So for all those for that particular key, we can have all the entries which are belonging to that key. That's the difference between the map and the multi-map. Now let's come to the container adapters. Container adapters are these are not as special, or the we can say the another STL containers, but they are the containers which are having some underlying containers. We can say a wrapper built on top of another STL container. Okay, that restricts the operations to behave in a specific way. We will just see in more detail. As we have already discussed about the stack queue and priority queue, let's go more deeper into this. So stack queue and priority queue, these three are the container adapter types. Container adapter types means, here we can see that stack firstly. Stack is using the default underlying container DQ, and it can also use the vector or list. Firstly, why it is using DQ? Let's uh, firstly think of this. See, stack is using the underlying default container as DQ because we already know that DQ is having the fastest operations. Like it can push or pop, it can from the front or end, both. So because of that, it is using the DQ. And in the stack, we already know that we have to only perform the operations from the one end. That is at the end itself. If we have to pop anything, if we have to take the top element, we have to push any element. Okay, that's why it is using DQ. It can also use vector or list because vector also is also having the one-ended operations like the push or pop. Okay. Now in the in the vector, at the end, one end is there from where we can push or add the elements. Now the behavior of a stack is, already we know that LIFO and all the push pop operations, top operation, these are all the having the time as the constant cost. Now in the queue, again it is using the default container underlying container as DQ. Okay, so it can also use list, but why it is not using vector? Because queue is some a container that it is having both the rear and front end. Okay, so it can perform their operations can be performed using DQ, but in the vector we already know that it is having only one end. But if we have, like at the end, but if we have to perform any operation for the front, it is taking worst case scenario for big O of n, and that is not at all quite good for using as a default underlying container for the queue. So that's why we are using the DQ here as a default underlying container, and also can use the list but not the vector. Now behavior is simple. FIFO operations are push, pop, and the front and back. Also already using the DQ. Okay, and time is constant again. Now seeing the priority queue. So priority queue is having the default underlying container as vector. See, priority queue is written something like this, and we are using priority queue. So it is written like priority queue, and inside this we give some of the parameters like integer, and then we give vector as a container, which is a default underlying container in this, and then we give something like comparators. Okay, whenever we are using based on what type we are using. If we are using the max heap, then we can just, sorry, this is for the min heap. Okay. and we are using min heap, because priority queue always, whenever we are using the priority queue, is it by default uses the max heap, so we do not have to give the lesser int there. This is for the min heap. We are just checking that how the priority queue is written. So this is we are saying that the we are seeing for the default container. So here vector is used as the default container, and its behavior is heap simple, and operations are push pop top, for the where the push and pop operations takes big O of login time, and the top operation takes a constant time, okay, which is the element at the root node. And yes, these are the vectors stack and queue. We are just seeing the difference, but that why the vector is not used in the this queue but used in the vector. So because the stack is needs the fast, so for the fast push and pop at one end, so the stack can use vector. So vector supports here, but vector do not supports in the case of queue, because here the at the back it takes constant, but for the front it takes big O of n. Okay, that's the difference. That rest you can just read from here. So that's a simple note that C++ uses the vector for the priority queue, which we already seen now, and because the random access is needed for the heap. Okay, that's the simple. That's all about these containers. Now, after the containers, just let's go into the iterators and also understand how these iterators perform on the containers. See, if we are not using the iterators, then for every container you will have to use the different forms in order to iterate over the containers. It can be like different forms, but in the iterator, what happens is that we use a simple line like this: for auto it equal to v dot begin, and it not equal to v dot end it plus plus. That this we will see. Just firstly look what are the iterator. Iterator is a kind of pointer like object, we can say, or the object that behaves like a pointer, okay, which is used to move through a container. So it's just a just think of a bookmark in a book. Like if a bookmark is there in a book and it is written that this particular page is this, you can directly go there, and if you have to just to go inside that, you can go inside that. It means a kind of in the case of values, if we are having a position, we can just go inside that using the dereferencing or using the star operator. So that's to get the value, we can use a star operator just to dereference the value at that position, and then to move forward we can use plus plus it. So this is an object that behaves like a pointer used to move through a container. Now, without the iterators, already I told that every container would need a different way to loop. But with iterators, by using this, we can simply walk through on any of the container. Using for auto it iterator equal to v dot begin, just go at the v dot begin. That is a starting position, and until you are not going at v dot end, it means the last position, where the last element is, just beyond next position after that last element. When you go, just stop there, and every time you can plus plus for that iterator. It works for the vector, set, map, list, unordered set, unordered map. Okay, some of the important points. Vector iterator, how it works. See, vector iterator here, it acts as a just a simple difference. Rest the iterators work same for all the containers. Okay, so important point is that for the vector iterator, it acts as a simple pointer, because vector stores the elements in a row. Here we are just having the difference between the contiguous and the non-contiguous memory. Okay, rest the iterator works for the same. So I in the vector, what we can do is we can just with the help of indexing, we can just go at every position, at every element. We can access okay, with the help of indexing. So if we are giving, if we are saying that if we are doing it plus 5, so that is available in the case of vector iterator, sorry, in the vector. But if we are saying, we're talking about the list, if we are doing it plus 5, that we can't do in the list, because it is not contiguous in the memory. Let's discuss more about this. See, in the vector, what happens is it is having the contiguous memory. So now if you are saying that it plus 5, now internally the what formula it is using, it is saying that we use the formula current address plus that index where we have to go, and multiply that with the size of the element. So this is how it is finding the memory, and that's because the memory is contiguous in the vector. So that's why it can go at that particular index. But in the case of list, if you are saying that it plus 5, it means you are saying that go to the 5, you just move on to the 5 steps ahead, and in the contiguous memory, because again it will be using the same formula. But because list is not having the contiguous memory, so it will not work in this. In the list, as we have already talked about, we will have to move one step at a time, one node at a time, because uh, what is happens is every element is having the data value, and it is having the address for the next node and for the previous node. So if it has to move forward, then it can move only to the one node, and that is also with the help of the next pointer, because it is having the address of the next node. So that's how it works. So in the vector, it works as it plus n, but in the case of list iterator, it works as it plus plus or it minus minus. Just remember this thing. And in the set or the map iterator, it moves to the BST in the sorted order, which we already discussed. First. Now, iterator types, there are three types of iterators: random access iterator, bidirectional iterator, and the forward iterator. Random access means in the case of vector and DQ, as we have already seen that. Also in the DQ, there is a contiguous memory. Just remember this, because in DQ, we cannot say that it is having a contiguous memory, but it is having the partial contiguous in the form of blocks. There are the multiple blocks of memories which are contiguous in nature. So that's why we are saying that it is the memory is contiguous enough that C++ can give the random access uh, operations in order to iterate on that particular data. So the random access is available in the case of vector and DQ containers, but in the bidirectional, it means it can go move both the directions. It can move forward, it can move backward. So it can not jump directly, but it can go back, yes, but in the list, map, and set. Also, and also in the multi set and multi map. That's also okay. And forward iterator, it can only move forward just in the case of unordered map and the unordered set. It cannot jump, it cannot go back, only forward. Now, why the list supports only plus plus it but not it plus one? That we already discussed. That why the list is only supporting plus plus it, because it is in the contiguous memory. It is not having the contiguous memory. The nodes are just scattered in the memory. So if we have to, if the particular list iterator, when we do this plus plus it, what it says is that, hey iterator, just move to the next node following the dot next pointer. Why dot next pointer? Because dot next pointer is having the address for the next node. That's why we are saying we cannot say here it plus one, because it will use the formula current address plus that particular index into the size of the element, which will take to the contiguous in the contiguous memory manner. But the node is not like it might present, but it is not valid. You cannot use that. So it's just like that. Node 1 is at some random memory, node 7 is at some random memory, so we cannot use. We will just use plus plus it or minus minus it, just one node at a time. Now real world analogy. Vector as a row of seats we can just think of, and list as the train apartments. See, in the vector, if we are just taking into consideration the row of seats, if I have to go at 37 number seat, I can just go directly there. Okay, but if we are in the list, we are saying that train compartments are there like A, B, C, D. If I am saying, if I am at A, if I am saying that go to C, I cannot jump directly. I will have to go one step at a time from A to B, then B to C. That's how it works. So IT plus n, IT minus n, IT of n, these operations can also be performed in the DQ, as I have already discussed about the block memory as the contiguous memory that is partially contiguous. So it is partially contiguous plus block indexing and also the random access. It means in the block indexing, what happens is we just know the index. I can just find that that particular index is present in which block, and inside that block, I will go to that block. Now I will find that which index is that. I will directly jump to that index inside that block. So these are the containers: vector, DQ, list, and these are the memory layouts for this. Like vector is contiguous, and DQ is blockwise contiguous, and list is not contiguous. And this is how the iterators work. IT plus one is allowed in vector, it is allowed in DQ, but it is not allowed in list. Okay, and pointer arithmetic, it is because in the pointer arithmetic, that is in the case of vector, block indexing in the case of DQ, but here the list follows the node pointers. When IT plus plus is done, it says that follow to the dot next pointer, which is having the address to the next node. This is all about the iterators. We have just seen that how they works on the containers. Okay, now let's talk about the algorithms. The most important part in STL, algorithms, that how what we can perform on the data, what operations we can perform, like sorting, like reverse the data, or just in case if we have to search anything, that's the different operations or the algorithms are there. So for the sorting, the sort function is there. We can just give the begin and the end, and it will use these all. It uses just these hybrid sort methods like quick sort, merge sort, heap sort. And if we have to reverse, we just use in most of our problems to solve. Reverse, like begin, dot, end we can give inside. Now coming to the lower bound and upper bound, which I have told. So just take an example. The array is having 1 2 4 4 4 7 9. Now lower bound of x, if I have to find, What is firstly lower bound of x? Lower bound of x means whatever is the x element. This is the array I am having. Whatever is the x element, which it can appear, is the first position where x can appear or x should appear. That particular position it gives, or we can say the index, a kind of it gives. So it is just a formula or a condition. We can say the first element in the array which is greater than or equal to x, that is the element from where at which this x should appear. Now there might be two cases: either the x will not appear, either the x will appear. So if that element is greater than or equal to x, so if it is equal to x, it means that element is present there. If it is greater than x, it means x should appear there, but it is not present as of now. And the upper bound of x means the first position from where the x can no longer appear. It means the first element which came as greater than the x. So that's the position from where x can no longer appear in the container. Now we have to find the frequency of x in the sorted array. So we can just perform this. We can use this formula, upper bound minus lower bound of x. It just to give the frequency, that how many number of times that element or x is appearing inside the array in the sorted array. Now what if when element is absent? Just think of this. What if the element is absent in the array? Then what will happen is, just think of that I have to find 3 here, or I have to check that yes, I have to find the lower bound of 3. So if the lower bound of 3, I am finding 3 for the 3, so x is equal to 3. Now if any element is greater than or equal to 3, which element is 1? No. 2? No. 4? Yes, it is greater than or equal to 3. It means this is the position where x should appear, or okay, x should appear. But here it is greater than x, which I have already told that if any element is greater than x, it means x should appear here, but it is not. But it is not here. If the element is absent here, so lower bound will give a particular value for x, that is a position or the index. So here the 3 should appear at this particular index, 0, 1, 2, at 2 index. Okay, so whenever we are finding that this element should appear, let's say someone is asking that we are finding the element 3 in the array. Now what if the element 3 is not absent there? Lower bound will give an index, and with that index you can just compare your key or whatever it is, and if it is not equal, then obviously the element is not present. That's the thing, simple thing. Now simple checklist: we have seen what is lower bound, we have seen what is upper bound, we have seen what are the insertion points. It means whenever we have to see that yes, this particular element should appear here, that's the case. Now how to find the frequency, that we have already seen. How they behave when element is absent, that we have already seen. Now coming to the binary search, now we will see that how this particular trio works, like lower bound, upper bound, and the binary search. So binary search basically returns the lower bound of x. What is the lower bound of x gives? It gives the index that where the x point, or we can say the iterator, like where this particular x should belong or should appear. That the binary search gives that index. If it is binary search gives the true or false, if it is present or not. But just return that particular thing. Now binary search, it works on the sorted array. We can jump directly to the mid for seeing the particular key for which we are searching, throw away half each time, and we can that particular operations are performing login. It's like a dictionary, simple. Just understand, we are having a dictionary and I'm finding a word, let's say a tiger. I know that it will be present at a page where the words starts with t. Now I will not do such thing that I will go in the dictionary, I will open the first page, I will start from checking a words, then b words, starting letters. I will directly open the dictionary at the middle or somewhere. If I found that yes, this page is containing the words which are starting from M, I know that T comes later after M. I will not go to the previous half. I will just remove that or just discard that, and I will go to the next half, whatever it is remaining in the dictionary. Then I will see for those words which are starting, and this is how I will repeat the process till I am not finding a page where the words starts with T. That's how the binary search works. Binary search tells if x exists, true or false. Lower bound tells where x could be inserted. So as upper bound tells that where the x stops appearing. That we have already seen. Binary search is the yes or no function, and lower bound or upper bound, they are the location functions. Okay, so this is the simple. Now you can ask that how the lower bound and upper bound works in the binary search. See, what happens is, whatever the key we are searching for using the binary search, what will the lower bound do? Lower bound will find that particular key. Now it will just tell that it should appear here, and it will give that particular index. So if it is giving that particular index, that yes, let's say this is my array and I'm finding the key 3. So now 3 is present here. So if the what the index will give, that lower bound, it will give the index 0 1 2. It will give the index 2, that 3 should appear here because it is greater than or equal to 3. So it will give this particular index, and after the from this particular index, whatever the element is present, it will give that element, and it will compare with the key with which we are with which we have to find it is present or not. And if these both are equal, it means the element is present, otherwise it is not present. That's how the these call works along together. So this trio solves many problems, like if we have to check if x exists, like the binary search, we will just give v dot begin, v dot end, and give the key in order to search that in the container. Then to count the frequencies, we have just seen the formula, that frequency for the upper bound of x minus lower bound of x. And if we have to find the insertion index, then in that case we can just use this formula, like to get the index we will just use lower bound of x minus v dot begin. This will give us the index in order to find that insertion index where we can insert the element. Now there are some more algorithms. First is the find, which is used to now find is not something that it will directly find the element. It will basically give a iterator, or the position where that element is appearing or present. So that takes big O of n, because that sees linearly, like one by one. So find function, it returns an iterator, it not returns an index. And its simple meaning is that it returns a pointer like object pointing to the found element. And then if we want to get at that element, we can just use the point, the star or something, in order to get that position, to like dereferencing. And if the element is not found, then it returns container dot end. At whatever the container is, dot end means the position just next to the last element. And auto it, that is equal to just find v dot begin, v dot end, and dot 30. It means we have to find the 30, then we can just use this, and it will give the iterator, which will be stored in it. Now to get the int index, if we want to, now it is giving the iterator where the element is belonging or the appearing. Now if we want to get that particular index, then we can use this it minus v dot begin. This we will use many times. Now it is only possible in the case of vector, dq, or array, because they are having the contiguous memory. Now coming to the max element, min element, and accumulate. Again, if we are finding the max element, it will not give us directly the max element. If we are finding the min element, it will not give that directly the min element. What we will have to do is, it means what they do is, they give us the iterator to that position where the max element belongs. It gives the iterator to that position where the min element belongs. So that's how the max and min element this function works. So max element, that is again taking big O of n cost, and the min element is again taking big O of n cost. So here, if this is the vector and if we have to find the max element, what it will give, it will give the iterator to the position where the 9 is appearing. And if I have to find that element, I will just I will just take that element, that maximum, inside the max variable using dereferencing. It is giving me the pointer, that is iterator, and I will go at that iterator and take that element, that is 9. That's the maximum element. Same in the case of min element. Okay, it just gives the minimum element. Then accumulate, how the accumulate works. So accumulate is see what we do when we are having an array. So we just if we want to sum up all those elements which are present in the array, we just run a loop in order to sum all those values. So accumulate, what it do is, it is a shortcut for the loop which we use. It adds all the elements for a range and returns the total. So just imagine that you are having a vector, and you are having a vector which is having elements 5, 10, 15. Now let's say if you have to sum all these elements, what you will do, you will simply run a loop. You will just initialize the sum variable with the 0, and then you will just run a loop for int x, like int x, for each loop, int x colon v, where you will just sum all the values inside the sum variable. But accumulate, what it does is, it just is a shortcut for that loop. It writes in this way: it gives the starting iterator, it gives the end iterator, and it gives the initial value. Initial value is the value which we are giving inside the sum at a start as 0. That initial value comes as 0 in the accumulator as a third parameter, we can say. So for example, int sum uh, equal to accumulate, and this v dot begin, v dot end, and 0. So this is how it works, and whatever the value will come as sum, it will just store in the some variable. Okay, so that's all about this standard template library. We have seen way more about this standard template library, and we have just seen all types of containers. We have seen the container adapters, and we have then seen the iterators, that how they perform on the containers. Okay, and then we have also seen some important concepts which are also a kind of hidden if we are not having the knowledge of those, and the STL algorithms, uh, where the different algorithms are there like and when I was learning, I found the lower bound and upper bound is most important, as I have understood how these works, lower bound, upper bound. So that's all about this video, and meet in the next video. Thank you.